Right now, at this very moment, you are being held gently but firmly against the surface of a spinning ball of rock hurtling through space at thousands of miles per hour, yet you feel perfectly still, perfectly secure. The force accomplishing this seemingly impossible feat is so fundamental to your existence that you never think about it, until something goes wrong with it, or until you pause, as we're about to do tonight, and realize that this most familiar force in the universe might also be its greatest mystery. Welcome to Sleep About Science. I'm your host, and tonight we're exploring the profound enigma of gravity mirrors, that invisible sculptor that shapes galaxies and guides raindrops, that bends light and stretches time, yet remains stubbornly mysterious to even our brightest minds. If you drift off to sleep while listening, that's perfectly wonderful. In fact, as we sink into the deep mysteries of this force, letting your mind drift might be exactly what we need. Before we begin, please make yourself comfortable. Get settled under your blankets, adjust your pillow, and let yourself sink into that sweet spot between alertness and rest. And remember, this is educational content designed to inspire wonder, not replace professional scientific instruction. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the profound puzzles that surround us every day. Now, let's begin our quiet exploration into the beautiful mystery of gravity, starting with perhaps the most fundamental question of all. We don't understand what gravity actually is. Oh, we can describe what it does with breathtaking precision. We can calculate exactly how fast an apple will fall from a tree, predict the orbit of a comet returning after centuries in the dark, even detect the ripples that massive black holes make when they collide billions of light years away. But the essential nature of gravity, what it fundamentally is, remains as mysterious today as it was to Newton when that legendary apple supposedly fell beside him under a tree. Einstein gave us a beautiful way of thinking about gravity, not as a force pulling objects together, but as the curvature of space-time itself. Imagine a stretched rubber sheet with a bowling ball placed in the center. The ball creates a depression, and marbles rolled across the sheet will curve toward it, not because the ball is pulling them, but because they're following the curved geometry of the sheet. This is Einstein's vision. Massive objects curve space-time, and what we experience as gravity is simply matter, following the straightest possible path through this curved geometry. But here's what we don't understand. Why does mass and energy curve space-time in the first place? Einstein's equations describe this curvature with mathematical perfection, but they don't explain the underlying mechanism. It's as if we have a perfect recipe for baking a cake, but no idea why flour and eggs and heat combine to create something entirely different from their individual parts. We don't understand why gravity is so incredibly weak compared to the other fundamental forces. If you've ever picked up a paper clip with a magnet, you've witnessed something extraordinary, a small magnet overcoming the gravitational pull of the entire Earth. The electromagnetic force that allows the magnet to attract the paper clip is roughly 10 to the 36th power times stronger than gravity. That's a number so large it's almost meaningless. Imagine writing the number 1 followed by 36 zeros. Why should gravity be so feeble? In the grand theatre of the universe, gravity seems to be the quiet stagehand working behind the scenes while the other forces, electromagnetic, strong nuclear, weak nuclear, perform dramatic feats in the spotlight. Yet this weakest force somehow manages to dominate the large-scale structure of the universe, binding solar systems, sculpting galaxies, and determining the ultimate fate of everything that exists. We don't understand why gravity can't be easily unified with quantum mechanics, the theory that describes the behavior of the smallest particles. Every other force in nature has been successfully incorporated into the quantum framework, but gravity stubbornly resists. When physicists try to apply quantum mechanics to gravity, their equations explode into nonsensical infinities. It's as if gravity speaks a completely different language from the rest of physics, leaving us like translators struggling to bridge two incompatible worlds. This isn't just an abstract mathematical problem, it has profound implications for our understanding of reality. Quantum mechanics tells us that empty space isn't empty at all, but seethes with virtual particles constantly popping in and out of existence. These quantum fluctuations should, by rights, create an enormous amount of gravitational force, but they don't. In fact, when physicists calculate how much gravitational effect these quantum fluctuations should produce, they get a number that's wrong by 120 orders of magnitude, possibly the worst prediction in the history of physics. We don't understand what happens to gravity at the center of black holes. As matter falls toward a black hole, general relativity predicts that it will eventually reach a point of infinite density and zero volume minus what physicists call a singularity. But infinity isn't a place or a thing you can visit. It's a mathematical concept that signals the breakdown of our theories. At the singularity, our understanding of gravity simply stops working, like a GPS that throws up its hands and declares, "I have no idea where you are." This isn't just academic speculation. Black holes definitely exist. We've photographed their shadows, detected the gravitational waves they produce when they merge, and watched stars orbit around them like cosmic dancers. But at their very hearts, in those infinitely dense points where space and time become meaninglessly distorted, gravity becomes something we cannot comprehend. We don't understand whether gravity propagates at exactly the speed of light. Einstein's theory predicts that gravitational waves should travel at light speed, and our recent detection of these waves from colliding black holes seems to confirm this. But here's the puzzling thing. How does gravity know to travel at the speed of light? Light travels at light speed because photons are massless. But what is it about gravitational waves that gives them this same cosmic speed limit? Moreover, we don't understand what would happen if gravity traveled at a different speed, if gravitational changes propagated instantaneously. As Newton believed, the universe would be a very different place. If they traveled slower than light, planetary orbits would spiral inward. If they traveled faster, planets might spiral outward. The fact that gravity propagates at exactly the right speed to keep the universe stable seems almost too convenient to be accidental. We don't understand dark matter, which appears to be the gravitational scaffolding upon which the entire visible universe is built. When astronomers look at galaxies, they find that stars are orbiting much too fast for the amount of visible matter they can detect. According to our understanding of gravity, these stars should fly apart like sparks from a pinwheel. Instead, they remain bound in stable orbits, suggesting that there's about 5 times more matter in the universe than we can see. This invisible dark matter doesn't emit or absorb light. It seems to interact with ordinary matter only through gravity. It's as if the universe is mostly made of gravitational ghosts, invisible masses that shape the cosmic architecture, but remain forever hidden from our direct observation. We've built sophisticated detectors buried deep underground, hoping to catch a dark matter particle in the act of colliding with an atomic nucleus. But so far, these cosmic phantoms have remained elusive. Even more mysteriously, we don't understand dark energy, the force that appears to be accelerating the expansion of the universe itself. In 1998, astronomers studying distant supernovae made a shocking discovery. The universe isn't just expanding, it's expanding faster and faster. Something is working against gravity on the largest scales, stretching space itself with increasing vigor. We call this mysterious agent dark energy. But that name reveals our ignorance more than our knowledge. Dark energy appears to make up about 68% of the universe, yet we have no idea what it is. Is it a property of empty space itself? Is it a new kind of field permeating the cosmos? Is it a sign that our understanding of gravity breaks down at enormous scales? We simply don't know. We don't understand why gravity seems to follow an inverse square law, why gravitational force decreases with the square of distance rather than some other mathematical relationship. If you double the distance between two masses, the gravitational force becomes 4 times weaker, triple the distance, and it becomes 9 times weaker. This precise mathematical relationship allows planets to maintain stable orbits and keeps the universe from either collapsing in on itself or flying apart immediately. But why this particular relationship? In a universe with different spatial dimensions, gravity would follow different mathematical rules. In 2 dimensions, it would be an inverse linear relationship. In 4 spatial dimensions, it would be an inverse cube relationship. The fact that we live in a universe with exactly 3 spatial dimensions, giving rise to exactly the right form of gravity to allow complex structures like stars and planets and ultimately life to exist, seems remarkably fortuitous. We don't understand whether gravity has always behaved the same way throughout cosmic history. The gravitational constant, number, that determines the strength of gravitational attraction is assumed to be truly constant, unchanging across billions of years. But what if it isn't? What if gravity was stronger or weaker in the early universe? Such changes could help explain some of the puzzling features we observe in cosmic evolution, from the formation of the first stars to the current acceleration of cosmic expansion. Some theories suggest that fundamental constants might slowly drift over cosmic time, like a radio slowly losing its tuning. If gravity has been gradually weakening, it might explain why the universe's expansion is accelerating. If it's been growing stronger, it might help account for the rapid formation of large-scale structure in the early cosmos. But detecting such tiny changes over billions of years requires measurements of extraordinary precision, and so far the evidence remains inconclusive. We don't understand whether there might be additional dimensions beyond the familiar three of space and one of time. Some theories in physics suggest that our universe might be like a thin membrane floating in a higher dimensional space, with gravity able to leak between these dimensions while other forces remain confined to our familiar four-dimensional spacetime. If extra dimensions exist, gravity might behave differently at very small scales than we expect. Instead of continuing to follow the inverse square law down to infinitesimally small distances, gravitational force might become much stronger when objects get closer than about a millimeter apart. Experiments using tiny masses and sensitive force detectors have searched for such deviations, but so far gravity appears to behave exactly as Einstein predicted, even at the smallest accessible scales. We don't understand why antimatter appears to respond to gravity in the same way as ordinary matter. In principle, antimatter might fall upward instead of downward, experiencing gravitational repulsion rather than attraction. If this were the case, it could help explain the cosmic acceleration we attribute to dark energy. Perhaps the universe contains hidden reservoirs of antimatter that create gravitational repulsion on large scales. But creating and studying antimatter is extraordinarily difficult. Antimatter particles annihilate instantly when they touch ordinary matter, releasing tremendous energy. The largest amounts of antimatter ever created on Earth consist of just a few trillion antiprotons, still far too few to detect their gravitational behavior directly. Physicists have developed ingenious indirect methods to study how antimatter responds to gravity, but definitive answers remain just beyond our current capabilities. We don't understand whether gravity might be different in regions of the universe far from our local cosmic neighborhood. Our solar system occupies a fairly typical region of a fairly typical galaxy, but the universe is vast beyond imagination. Perhaps in the hearts of galaxy clusters, where dark matter densities reach extreme values, gravity behaves in subtle ways we haven't yet detected. Perhaps in cosmic voids, where matter is vanishingly rare, gravitational effects follow slightly different rules. The cosmic microwave background, the afterglow of the Big Bang that pervades all of space, provides our best window into the early universe. But even this ancient light tells us mainly about conditions when the universe was already several 100,000 years old. The truly primordial era when quantum effects of gravity might have dominated remains largely opaque to our observations. We don't understand whether black holes eventually evaporate completely or leave behind some form of remnant. Stephen Hawking's theoretical work suggests that black holes should slowly radiate away their mass through a process now known as Hawking radiation. According to this theory, a black hole gradually becomes smaller and hotter as it evaporates, eventually disappearing in a final burst of energy. But this process leads to a profound puzzle known as the information paradox. If a black hole forms from the gravitational collapse of matter and then completely evaporates, what happens to the information that originally went into creating that matter? Quantum mechanics tells us that information cannot be destroyed, but general relativity seems to suggest that it disappears forever into the black hole and then vanishes when the black hole evaporates. Some physicists propose that black holes don't completely disappear, but leave behind tiny remnants that somehow preserve all the information that fell into them. Others suggest that information might escape slowly through subtle correlations in the Hawking radiation. Still others propose more radical solutions, such as the idea that the interior of a black hole is connected to another region of spacetime through a wormhole. All of these possibilities challenge our understanding of how gravity behaves under the most extreme conditions. We don't understand whether the universe might undergo cycles of expansion and contraction, with gravity eventually overcoming dark energy to pull everything back together in a big crunch, only to have the cycle begin again. Alternatively, if dark energy continues to dominate, the universe might expand forever, with gravity gradually losing its ability to hold structures together as space itself stretches beyond all bounds. In such a far future, gravity might become so diluted by cosmic expansion that even atoms could no longer hold together. Alternatively, if dark energy itself evolves over time, it might eventually weaken, allowing gravity to reassert its dominance and pull the universe back toward collapse. The ultimate fate of everything depends on the long-term behavior of these two cosmic antagonists, gravity and dark energy, locked in an eternal struggle whose outcome we cannot predict. We don't understand whether gravity might allow for the existence of closed time-like curves, paths through space-time that loop back to their own beginning, potentially allowing for time travel to the past. Einstein's equations don't forbid such exotic space-time geometries, but they would require forms of matter and energy with very strange properties, such as negative energy density. If such time-traveling paths exist, they might be created through the manipulation of rotating black holes, or through the construction of traversable wormholes, tunnels, through space-time connecting distant regions. But any attempt to create or use such structures would likely require precise control over gravitational fields far beyond our current technological capabilities. We don't understand whether the vacuum of space itself might have gravitational properties we haven't yet discovered. Empty space, according to quantum field theory, is actually a seething foam of virtual particle pairs continuously appearing and disappearing. This quantum vacuum might possess an energy density that contributes to gravity, but calculating this contribution leads to those infamous infinities that plague attempts to unite gravity with quantum mechanics. Some theories suggest that what we call the cosmological constant, minus the energy density associated with dark energy, might actually be the gravitational manifestation of quantum vacuum effects. If so, understanding the true nature of empty space might be the key to solving one of cosmology's greatest puzzles. We don't understand whether gravity might emerge from some more fundamental phenomenon, rather than being a fundamental force in its own right. Just as temperature emerges from the random motions of molecules, gravity might emerge from the collective behavior of some deeper level of reality that we haven't yet discovered. Some theories propose that gravity arises from the entanglement of quantum information across space-time, that the very fabric of space-time might be woven from quantum correlations between distant regions. Others suggest that gravity might be a thermodynamic phenomenon, related to the flow of information and energy through cosmic horizons. If such ideas prove correct, our entire picture of gravity as a fundamental force might need to be reconsidered. We don't understand why the geometry of space-time near massive objects leads to phenomena like frame dragging, where rotating masses literally twist the fabric of space around them like honey stirred by a spoon. This effect, predicted by Einstein but only recently confirmed through precise measurements using orbiting gyroscopes, reveals that space itself can be set into rotation by massive spinning objects. The implications are profound. Near a rotating black hole, there exists a region called the ergosphere, where space-time itself is dragged around so violently that nothing minded, not even lighted, can remain stationary relative to a distant observer. Understanding how mass-energy curves space-time is one thing. Understanding how rotation imparts angular momentum to space-time itself opens entirely new dimensions of mystery. We don't understand whether gravitational waves might carry information beyond the simple patterns of compression and expansion that our detectors currently measure. These ripples in space-time, created when massive objects accelerate, have opened an entirely new window for observing the universe. But what if gravitational waves have subtle features we haven't yet learned to detect, might just polarizations or frequency modulations that could reveal new aspects of how gravity propagates through the cosmos? Our current gravitational wave detectors are sensitive to changes in length, smaller than 1/10,000th, the width of a proton, yet they can only detect gravitational waves within a limited frequency range. Lower frequency waves might reveal different types of cosmic events, while higher frequency waves might carry signatures of exotic physics occurring at the moment of black hole formation. We don't understand whether gravity might have played a crucial role in the very earliest moments after the Big Bang, when the universe underwent a period of rapid expansion called cosmic inflation. During this epoch, quantum fluctuations in the gravitational field might have been stretched to cosmic proportions, eventually becoming the seeds from which all cosmic structure, minima, galaxies, clusters of galaxies, even the cosmic web itself, eventually grew. But the physics of inflation remains largely theoretical. We don't know what caused it, what sustained it, or exactly how it ended. Some versions of inflation theory predict that it should have produced gravitational waves with specific characteristics, but detecting these primordial gravitational waves requires measurements at the very edge of current technological capabilities. We don't understand whether there might be multiple universes with different gravitational properties, each arising from different solutions to Einstein's equations, or different ways that gravity might be unified with quantum mechanics. In some theoretical frameworks, our universe might be just one bubble in an infinite foam of cosmic bubbles, each with its own laws of physics and its own version of gravity. If such a multiverse exists, most universes might have forms of gravity incompatible with the existence of stars, planets, or life. We might live in one of the rare cosmic lottery tickets, where gravity happens to have just the right properties to allow complex structures to form and persist. But testing such ideas requires grappling with questions about what it even means for something to exist, if it can never be observed or verified. We don't understand how gravity behaves during the collision of neutron stars, those incredibly dense remnants of collapsed massive stars where a teaspoon of matter weighs as much as a mountain. When two neutron stars spiral into each other, they create conditions so extreme that ordinary matter becomes an exotic soup of quarks and gluons, the fundamental building blocks of protons and neutrons. In such environments, gravity must compete with nuclear forces operating at their absolute limits. The resulting gravitational waves carry signatures of how matter behaves under conditions that cannot be replicated in any terrestrial laboratory. Each neutron-star collision we detect teaches us something new about the interplay between gravity and the strong nuclear force in regimes where both approach their theoretical extremes. We don't understand whether the phenomenon we call gravitational lensing, the bending of light by massive objects, might have subtle features we haven't yet detected. When light from distant galaxies passes near massive galaxy clusters, it's bent and focused like light passing through a cosmic magnifying glass, sometimes creating multiple images of the same distant object. But what if gravitational lensing doesn't affect all forms of light equally? What if certain frequencies of electromagnetic radiation follow slightly different paths through curved spacetime? Such effects would be incredibly tiny, but they might reveal new aspects of how gravity interacts with other fundamental forces. We don't understand why some solutions to Einstein's equations predict the existence of exotic objects like naked singularities, regions of infinite density that aren't hidden behind black hole event horizons. Most physicists believe that nature somehow prevents such objects from forming through a mechanism called cosmic censorship that ensures all singularities remain safely hidden from the outside universe. But we don't understand what physical principle might enforce cosmic censorship, or whether it might fail under certain extreme conditions. If naked singularities could exist, they would represent regions where the known laws of physics break down completely, potentially allowing for phenomena like time travel or violations of causality. We don't understand whether gravity might allow for the existence of stable configurations of pure gravitational energy through regions of curved spacetime that persist without any matter or energy to support them. Such gravitational solitons would represent a kind of knot tied in the fabric of spacetime itself, maintained by the non-linear interactions between different components of the gravitational field. Finding such objects would require detecting regions of space where the geometry is curved despite the apparent absence of any source of curvature, a challenging observational problem that pushes the limits of our current understanding of both gravitational theory and observational astronomy. We don't understand how gravity might be modified by the presence of exotic forms of matter that might exist only in the most extreme environments. Certain theories predict the existence of strange matter, composed of quarks in configurations that don't occur in ordinary atomic nuclei. If strange matter exists, its gravitational effects might differ subtly from those of ordinary matter. Similarly, magnetic monopoles, hypothetical particles with only one magnetic pole rather than the usual north-south pair, would have unique gravitational signatures if they exist. Detecting such exotic particles through their gravitational effects might be easier than detecting them through electromagnetic interactions, but it would require gravitational measurement techniques far more sensitive than anything currently available. We don't understand whether the expansion of space itself might be affecting the strength of gravitational interactions on local scales. As the universe expands, the average density of matter decreases, potentially changing the large-scale gravitational environment in which local gravitational interactions take place. Some theories suggest that such cosmological effects might very gradually change the strength of gravitational interactions in bound systems like solar systems or galaxies. Detecting such changes would require monitoring gravitational phenomena with extraordinary precision over many years, comparing current measurements with the most accurate observations from previous decades. We don't understand whether gravity might be transmitted by particles as the other fundamental forces are, or whether it represents a purely geometric property of spacetime that doesn't require particle mediators. Quantum field theory suggests that gravity should be carried by particles called gravitons, but these hypothetical particles have never been directly detected. Gravitons, if they exist, would be massless particles traveling at the speed of light, but they would interact so weakly with ordinary matter that detecting individual gravitons would be virtually impossible with any conceivable technology. This leaves us in the peculiar position of having a detailed mathematical description of how gravitational particle interactions should work, but no practical way to verify whether this description corresponds to physical reality. We don't understand whether black holes might serve as gateways to other regions of space-time connected through wormhole tunnels that allow matter and information to travel vast distances instantaneously. Some solutions to Einstein's equations do predict such connections, but they would require forms of matter with negative energy density to remain stable. Creating or finding such wormholes would revolutionize our understanding of cosmic geography, potentially allowing communication or even travel between distant parts of the universe. But the exotic matter required to hold wormhole throats open would need to violate several fundamental assumptions about the behavior of matter and energy. We don't understand whether the apparent fine-tuning of gravitational strength, the fact that gravity seems to have exactly the right strength to allow stars and galaxies to form, represents a genuine puzzle requiring explanation or merely an observational selection effect. If gravity were significantly stronger, stars would burn out quickly and black holes would be much more common. If it were significantly weaker, matter might never have been able to clump together to form stars at all. This apparent fine-tuning might be explained by the existence of multiple universes with different gravitational strengths, with life only arising in those rare universes where gravity has values compatible with cosmic structure formation. Alternatively, there might be deep physical principles we haven't yet discovered that require gravity to have its observed strength. We don't understand how the quantum mechanical concept of superposition, the ability of particles to exist in multiple states simultaneously, might apply to gravitational fields. If massive objects can exist in quantum superpositions, their gravitational effects should also exist in superposition, creating bizarre situations where space-time itself might be curved in multiple different ways simultaneously. Testing such ideas requires creating quantum superpositions of sufficiently massive objects that their gravitational effects become detectable. Current experiments can create superpositions of individual atoms or small molecules, but extending such techniques to objects large enough to produce measurable gravitational fields represents an enormous technological challenge. We don't understand whether the holographic principle, knows, the idea that all the information in a volume of space might be encoded on its boundary surface, applies to gravitational physics. Some theories suggest that gravity in three-dimensional space might be equivalent to a different kind of physics operating on a two-dimensional boundary, like a three-dimensional hologram encoded on a flat surface. If the holographic principle applies to gravity, it might provide new insights into the information paradox of black holes and offer clues about how to unite general relativity with quantum mechanics. But translating between the three-dimensional and two-dimensional descriptions of gravitational phenomena remains a formidable theoretical challenge. We don't understand whether gravitational interactions might be fundamentally asymmetric in ways we haven't yet detected. While Einstein's theory treats gravitational attraction symmetrically, the Earth pulls on the Moon with exactly the same force that the Moon pulls on the Earth. Some alternative theories of gravity predict tiny violations of this symmetry. Such violations would be extraordinarily small, but they might be detectable through precision measurements of planetary motions or through laboratory experiments with carefully balanced masses. Discovering gravitational asymmetries would require revising our most basic assumptions about the nature of space-time and the principle of equivalence that underlies general relativity. We don't understand how gravity might behave in the presence of rapidly rotating reference frames or strong electromagnetic fields. Einstein's theory predicts various subtle effects in such situations, but testing these predictions requires creating extreme conditions that push the boundaries of experimental technique. For instance, laboratory tests of how gravity behaves in strong magnetic fields require precise measurements of tiny forces in the presence of much larger electromagnetic effects. Similarly, tests of gravitational effects in rotating reference frames must account for a host of subtle mechanical and electromagnetic influences that can easily overwhelm the gravitational signals being studied. We don't understand whether the cosmic web NINALs, the largest scale structure of the universe, consisting of vast filaments of dark matter connecting galaxy clusters, might have gravitational properties beyond those predicted by standard theories. The cosmic web represents gravitational architecture on scales of hundreds of millions of light-years, where our theoretical understanding becomes increasingly uncertain. Recent simulations suggest that the cosmic web might focus gravitational waves in ways that could amplify or distort signals from distant sources. Understanding such effects requires modeling gravitational interactions across enormous scales, while accounting for the complex distribution of both visible and dark matter. We don't understand whether gravity might be affected by the quantum mechanical process of measurement, whether the act of observing a gravitational field might somehow change its properties. In quantum mechanics, measurement plays a fundamental role in determining physical reality, but extending such ideas to gravitational physics raises profound conceptual challenges. If gravitational fields exist in quantum superpositions until they're measured, then the geometry of space-time itself might remain undetermined until some form of gravitational measurement takes place. Understanding what constitutes a measurement of a gravitational field and how such measurements might affect the field being measured requires grappling with some of the deepest interpretive questions in quantum mechanics. We don't understand whether there might be forms of matter that interact with gravity, but not with any other fundamental forces, essentially gravitational analogues of dark matter, but even more exotic. Such matter would be detectable only through its gravitational effects, making it extraordinarily difficult to study directly. Theoretical physics suggests that certain hypothetical particles, such as axions or sterile neutrinos, might have such properties. If they exist in sufficient quantities, they could contribute to cosmic structure formation in ways that differ from ordinary dark matter, potentially helping to explain some puzzling features in the observed distribution of galaxies and galaxy clusters. We don't understand how gravity might affect quantum entanglement, the mysterious connection between particles that allows them to influence each other instantaneously across arbitrary distances. If entangled particles are placed in different gravitational environments, their quantum correlation might be affected in ways that reveal new connections between gravity and quantum mechanics. Recent theoretical work suggests that space-time geometry and quantum entanglement might be intimately related, with the curvature of space emerging from patterns of quantum entanglement between different regions. If such ideas prove correct, understanding gravity might require understanding the quantum information structure of spacetime itself. We don't understand whether cosmic inflation in the period of rapid expansion in the early universe might have created regions with different gravitational properties that we haven't yet observed. Inflation theory predicts that our observable universe might be just one small patch of a much larger cosmic landscape, with different regions potentially having different physical laws. If such regional variation exists, we might eventually observe its effects through subtle anomalies in the cosmic microwave background, or through the detection of gravitational waves from cosmic events occurring in regions with different gravitational properties. But distinguishing such effects from other sources of cosmic variation requires extraordinarily precise observational techniques. We don't understand whether the apparent smoothness of space and time on large scales might break down in extreme environments, revealing an underlying granular or discrete structure. Some approaches to quantum gravity suggest that space-time itself might be composed of tiny, indivisible units, similar to how matter is composed of atoms. If space-time has such a discrete structure, it might become apparent in the propagation of gravitational waves from the most energetic cosmic events, potentially introducing tiny delays or distortions that could be detected by sufficiently sensitive instruments. However, the scale at which space-time discreteness might become apparent is likely to be far smaller than anything currently accessible to direct observation. We don't understand how the topology of space-its overall shape and connectivity might affect gravitational phenomena. While local physics appears to be the same everywhere, the global geometry of the universe remains largely unknown. Space might be finite but unbounded, like the surface of a sphere, or it might have exotic topological features like handles or twisted connections. Such topological effects might create subtle correlations in gravitational phenomena across vast distances, or they might affect the propagation of gravitational waves in ways that could be detected through careful analysis of signals from cosmic sources. Understanding the topology of space requires combining gravitational observations with sophisticated mathematical techniques from topology and geometry. We don't understand whether there might be gravitational analogues of the electromagnetic phenomena we observe in charged particle physics. Electromagnetism exhibits effects like electromagnetic induction and the generation of electromagnetic waves by accelerating charges. Gravity might have similar phenomena that we haven't yet recognized or learned to detect. For instance, rapidly changing gravitational fields might induce effects in nearby matter, similar to how changing magnetic fields induce electric currents, or there might be gravitational analogues of electromagnetic radiation pressure, subtle forces exerted by gravitational waves on the objects they encounter. Identifying and measuring such effects requires precision gravitational experiments at the very edge of current technological capabilities. We don't understand whether the equivalence principle, NITIR, the idea that gravitational and inertial mass are exactly equal, might be violated at some incredibly precise level. This principle forms the foundation of general relativity, but some quantum gravity theories predict tiny violations that might be detectable through sufficiently sensitive experiments. Testing the equivalence principle requires comparing the gravitational acceleration of different materials with extraordinary precision, looking for tiny differences that might reveal the underlying quantum mechanical structure of gravitational interactions. Current experiments have verified the principle to about 1 part in 10 trillion, but even more precise tests might reveal violations that could guide the development of quantum gravity theories. We don't understand how gravitational memory affects permanent changes in space-time geometry caused by passing gravitational waves might accumulate over cosmic timescales. When a gravitational wave passes through a region of space, it leaves behind tiny permanent displacements that persist long after the wave has gone. These memory effects are extraordinarily small for any individual gravitational wave, but they might accumulate over the billions of years that gravitational waves have been propagating through the universe. Understanding whether such cumulative effects might be detectable and what they might reveal about the history of gravitational wave sources throughout cosmic evolution requires sophisticated theoretical calculations combined with extremely precise observational techniques. We don't understand whether gravity might play a role in determining the fundamental constants of nature, numbers like the speed of light, Planck's constant, and the electric charge of the electron that appear to be the same everywhere in the universe. Some theories suggest that these constants might actually be determined by the overall gravitational environment of the universe. If such connections exist, changes in the cosmic gravitational environment, caused by the expansion of the universe or the evolution of large-scale structure, might cause tiny drifts in the fundamental constants over cosmic time. Detecting such changes requires comparing precision measurements made at different epochs, a challenging observational program that spans decades of careful astronomical observation. We don't understand whether the phenomenon of gravitational redshift, the way light loses energy as it climbs out of gravitational wells, might have subtle features that differ for different types of electromagnetic radiation. While all forms of light appear to be redshifted by the same amount in gravitational fields, some theories predict tiny violations of this universality. Testing such predictions requires comparing the gravitational redshift of different types of light with extraordinary precision, looking for tiny differences that might reveal how gravity interacts with different fundamental particles. Such experiments must account for a host of systematic effects while achieving measurement precision far beyond what is required for most other physics experiments. We don't understand whether there might be preferred directions in space that affect gravitational interactions. The violations of the assumption that space is isotropic and that physical laws are the same in all directions. While the universe appears to be highly isotropic on large scales, some observations suggest possible statistical anomalies that might indicate preferred directions. If space has preferred directions, gravitational interactions might be slightly stronger or weaker along certain axes, potentially affecting the orbits of planets and spacecraft in detectable ways. Searching for such effects requires analyzing orbital data with extraordinary care, looking for tiny systematic deviations from the predictions of standard gravitational theory. We don't understand how quantum fluctuations in the gravitational field itself might affect the behavior of matter and energy. Just as electromagnetic fields exhibit quantum fluctuations that can be detected through phenomena like the Casimir effect, gravitational fields should also exhibit quantum fluctuations that might have observable consequences. Such gravitational quantum effects might affect the behavior of atomic clocks in subtle ways, or they might contribute to the noise observed in gravitational wave detectors. Understanding and measuring quantum gravitational fluctuations would provide crucial insights into the quantum nature of space-time itself. We don't understand whether gravity might exhibit phase transitions, sudden changes in behavior similar to how water turns to steam, or how certain materials become superconducting at low temperatures. Some theories suggest that under extreme conditions, the nature of gravitational interactions might change discontinuously. Such gravitational phase transitions might have occurred during the early evolution of the universe, potentially leaving observable imprints in the cosmic microwave background or in the distribution of cosmic structure. Alternatively, they might occur in extreme environments like the interiors of neutron stars, where matter reaches densities comparable to atomic nuclei. We don't understand whether the concept of gravitational entropy, a measure of the information content of gravitational fields, might provide new insights into cosmic evolution and the nature of black holes. Just as thermodynamic entropy measures the disorder in physical systems, gravitational entropy might measure the complexity of space-time geometry. Understanding how gravitational entropy changes over time might help explain the arrow of time in cosmology and provide new perspectives on why the universe began in a state of low entropy that has been steadily increasing ever since. Such investigations require combining insights from general relativity, thermodynamics, and information theory in novel ways. We don't understand whether there might be fundamental limits to how precisely gravitational fields can be measured, similar to quantum mechanical uncertainty principles that limit simultaneous measurements of particle properties. Such gravitational uncertainty relations might place fundamental constraints on our ability to probe the quantum nature of space-time. If gravitational uncertainty relations exist, they might explain why attempts to measure gravitational effects at very small scales encounter fundamental limitations, not just technological ones. Understanding such limitations might provide crucial guidance for designing experiments to test quantum gravity theories. We don't understand how the phenomenon of gravitational dragging the way massive rotating objects drag space-time around with them, might affect the propagation of information and causal relationships near rapidly spinning massive objects. In extreme cases, such frame dragging might create regions where the usual ordering of cause and effect becomes ambiguous. Understanding how information and causality behave in such environments requires combining general relativity with information theory and quantum mechanics in sophisticated ways. The results might have implications for our understanding of black hole physics and for the fundamental nature of time itself. We don't understand whether gravitational interactions might be affected by the global structure of the universe, whether the presence of distant matter and energy might influence local gravitational phenomena in ways that standard theories don't predict. Some alternative theories of gravity include such non-local effects, where events in one part of the universe instantly influence physics everywhere else. Testing for non-local gravitational effects requires comparing precision measurements made at different times, as the configuration of distant matter changes due to cosmic expansion and large-scale structure evolution. Such tests must be designed carefully to distinguish genuine non-local effects from other sources of temporal variation in gravitational phenomena. We don't understand whether the vacuum of space might have a complex structure that affects gravitational propagation in ways we haven't yet detected. Quantum field theory suggests that empty space contains virtual particle pairs and quantum fields, but the gravitational effects of these quantum vacuum phenomena remain largely theoretical. Some theories predict that gravitational waves might interact with the quantum vacuum in ways that slightly alter their propagation speed or polarization. Detecting such effects would require comparing gravitational wave signals from sources at different distances, looking for tiny systematic differences that might reveal the quantum structure of spacetime. We don't understand whether gravitational interactions might exhibit memory effects, ways that the history of gravitational disturbances might affect current gravitational fields. Such memory effects could arise from the nonlinear nature of Einstein's gravitational field equations, which allow gravitational waves to interact with themselves. Understanding gravitational memory requires sophisticated mathematical techniques for solving nonlinear differential equations, combined with precision observational techniques for detecting tiny persistent changes in spacetime geometry. Such investigations might reveal new aspects of how information is stored and transmitted through gravitational fields. We don't understand whether the phenomenon of gravitational lensing might be affected by quantum mechanical properties of light, such as its particle-like nature, or its quantum entanglement properties. Most calculations of gravitational lensing treat light as classical electromagnetic waves, but the quantum nature of light might introduce subtle corrections. Testing for quantum effects in gravitational lensing requires comparing observations of lensed light with theoretical predictions that account for quantum mechanics, a challenging calculation that must consider how quantum properties of photons are affected by their passage through curved spacetime. We don't understand how gravitational fields might affect the quantum mechanical process of decoherence, the way quantum superpositions decay into classical behavior through interaction with the environment. If gravity can cause quantum decoherence, it might place fundamental limits on the ability to maintain quantum coherence in large-scale systems. Understanding how gravity affects quantum decoherence could provide new insights into why the classical world emerges from quantum mechanics, and might help explain why we don't observe macroscopic quantum superpositions in everyday life. Such investigations require combining gravitational physics with quantum information theory in novel theoretical frameworks. We don't understand whether gravity might have fractal properties, self-similar patterns that repeat at different scales from the quantum realm to cosmic dimensions. Some approaches to quantum gravity suggest that spacetime itself might have a fractal structure, with similar geometric patterns appearing, whether we examine space at the scale of atoms or at the scale of galaxies. If spacetime is fractal, it might affect how gravitational waves propagate across cosmic distances, or how matter behaves near the event horizons of black holes. Understanding such fractal geometry requires developing new mathematical tools for describing space and time that go far beyond the smooth curved geometries of Einstein's theory. We don't understand whether the phenomenon of gravitational chaos, the way gravitational systems can exhibit unpredictable behavior despite being governed by deterministic laws, might play a crucial role in cosmic evolution. Even simple gravitational systems like three bodies orbiting each other can exhibit chaotic dynamics that make long-term predictions impossible. On cosmic scales, gravitational chaos might affect the formation of planetary systems, the evolution of galaxy clusters, or even the large-scale structure of the universe itself. Understanding how chaotic gravitational dynamics shapes cosmic evolution requires developing new computational techniques for modeling complex gravitational systems over cosmic timescales. We don't understand whether there might be gravitational analogues of solitons, stable wave-like solutions that maintain their shape as they propagate through space. Such gravitational solitons could represent localized distortions in spacetime that travel without changing form, potentially carrying information across cosmic distances. If gravitational solitons exist, they might be created by certain types of cosmic events and could persist for billions of years as they travel through the universe. Detecting such exotic gravitational waves would require developing new analysis techniques for identifying persistent, shape-preserving disturbances in gravitational wave data. We don't understand how the quantum mechanical principle of complementarity myth-theory, the idea that quantum systems can exhibit mutually exclusive properties depending on how they're observed, might apply to gravitational phenomena. Different ways of measuring gravitational fields might reveal incompatible aspects of space-time geometry. Such gravitational complementarity might help explain some of the puzzles in black hole physics, where different observers can have fundamentally different descriptions of the same gravitational phenomena. Understanding these observer-dependent aspects of gravity requires developing new theoretical frameworks that can accommodate multiple, seemingly contradictory descriptions of the same physical situation. We don't understand whether the cosmic microwave background might be exhibiting subtle gravitational lensing effects that we haven't yet recognized. Distortions caused by the gravitational influence of dark matter structures that existed when this ancient light was emitted. Such primordial gravitational lensing might carry information about the earlier stages of cosmic structure formation. Detecting these effects requires analyzing the polarization patterns of the cosmic microwave background with extraordinary precision, looking for the subtle signatures that gravitational lensing would have imprinted on this ancient light. Such observations could provide unprecedented insights into the distribution of dark matter in the early universe. We don't understand whether there might be preferred reference frames in the universe, special coordinate systems where gravitational physics takes on particularly simple forms. While Einstein's theory is based on the principle that no reference frame is preferred, some quantum gravity theories suggest that certain frames might be naturally selected by quantum mechanical processes. If preferred reference frames exist, they might be detectable through subtle asymmetries in gravitational phenomena or through correlations between gravitational effects and the cosmic microwave background. Understanding such frame preferences could provide crucial insights into how gravity emerges from more fundamental quantum mechanical principles. We don't understand how the process of gravitational wave generation might be affected by quantum mechanical entanglement between the objects creating the waves. If two black holes spiraling toward each other become quantum mechanically entangled, their gravitational wave emission might exhibit correlations that don't exist in classical gravitational physics. Such quantum gravitational correlations might be detectable through careful analysis of gravitational wave signals from binary systems, looking for subtle patterns that reveal quantum mechanical aspects of gravitational dynamics. Understanding these effects could provide new ways to test the quantum nature of gravity using astronomical observations. We don't understand whether the phenomenon of gravitational birefringence, the possibility that gravitational waves with different polarizations might propagate at slightly different speeds, could reveal new aspects of spacetime structure. Just as light exhibits birefringence when passing through certain crystals, gravitational waves might exhibit similar effects when propagating through regions of curved spacetime. Detecting gravitational birefringence would require measuring the relative phases of different gravitational wave polarizations with extraordinary precision, looking for tiny delays that might accumulate over cosmic distances. Such measurements could reveal whether spacetime has a more complex structure than general relativity predicts. We don't understand how the global topology of the universe, its overall shape and connectivity, might affect local gravitational phenomena through subtle non-local correlations. If space has a complex topological structure with wormholes or other exotic connections, local gravitational measurements might be influenced by distant cosmic geometry. Such topological effects might manifest as subtle correlations between gravitational phenomena in different parts of the sky, or as tiny systematic deviations from the predictions of general relativity. Understanding these effects requires combining gravitational physics with sophisticated mathematical techniques from topology and geometry. We don't understand whether the vacuum energy of quantum fields might contribute to cosmic structure formation through gravitational effects that we haven't yet recognized. The quantum mechanical zero-point energy of fields should, in principle, create gravitational effects, but calculating these contributions leads to the infamous cosmological constant problem. If vacuum energy does contribute to gravity in ways we don't understand, it might affect the formation of cosmic voids, the clustering of galaxies, or the propagation of gravitational waves through empty space. Understanding these effects could provide new insights into the relationship between quantum mechanics and cosmic evolution. We don't understand whether there might be gravitational analogues of magnetic monopoles, hypothetical objects that would create gravitational fields with radically different geometries than those produced by ordinary mass distributions. Such gravitational monopoles might be created in extreme astrophysical environments or during phase transitions in the early universe. If gravitational monopoles exist, they would create distinctive signatures in gravitational wave detectors, and might help explain some puzzling features of cosmic structure formation. Understanding the properties of such exotic gravitational sources requires developing new theoretical frameworks for describing space-time geometries that go beyond Einstein's theory. We don't understand how the phenomenon of gravitational wave echoes, reflected or scattered gravitational waves that return to their source after interacting with cosmic structures, might reveal information about the large-scale distribution of matter in the universe. Such echoes could provide a new form of gravitational astronomy, allowing us to map cosmic structure through its effects on propagating gravitational waves. Detecting gravitational wave echoes requires developing new analysis techniques for identifying subtle delayed signals in gravitational wave data, distinguishing genuine echoes from noise and instrumental artifacts. Such techniques could open entirely new windows for studying cosmic structure and the properties of dark matter. We don't understand whether the process of cosmic inflation, the period of rapid expansion in the early universe, might have created gravitational structures that persist to the present day. Primordial gravitational waves from inflation might have evolved into complex gravitational field configurations that affect current cosmic dynamics. Such inflationary gravitational fossils might influence the formation of cosmic structure or create subtle correlations in the cosmic microwave background that we haven't yet recognized. Understanding these effects requires developing new theoretical tools for describing how gravitational perturbations evolve over cosmic timescales. We don't understand how the quantum mechanical measurement problem, meets the puzzle of how quantum superpositions collapse into definite classical outcomes, might be related to gravitational phenomena. Some theories suggest that gravity itself might be responsible for quantum wave function collapse, providing a natural mechanism for the emergence of classical behavior. If gravity does cause quantum collapse, it might place fundamental limits on the size and complexity of quantum systems, potentially explaining why macroscopic objects behave classically. Understanding this connection could provide new insights into both quantum mechanics and gravitational physics. We don't understand whether the apparent acceleration of cosmic expansion might be caused by back-reaction effects, the way small-scale gravitational dynamics might affect large-scale cosmic evolution. The complex gravitational interactions within galaxy clusters and cosmic voids might create collective effects that mimic the influence of dark energy. Such gravitational back-reaction might explain cosmic acceleration without requiring new forms of matter or energy, but calculating these effects requires solving Einstein's equations for realistic cosmic matter distributions, a computational challenge that pushes the limits of current theoretical techniques. We don't understand how gravitational effects might influence the fundamental constants that govern electromagnetic and nuclear interactions. Some theories suggest that the strength of electromagnetic forces or the masses of fundamental particles might be affected by the local gravitational environment. If such gravitational influences on fundamental constants exist, they might be detectable through precision spectroscopy of atoms in different gravitational environments, looking for tiny shifts in atomic energy levels that correlate with gravitational field strength. Understanding these effects could reveal deep connections between gravity and the other fundamental forces. We don't understand whether the phenomenon of gravitational wave memory The permanent displacement of test masses after a gravitational wave has passed might accumulate over cosmic time to create large-scale distortions in the geometry of space. Billions of years of gravitational wave propagation might have left permanent imprints on the fabric of spacetime. Such cumulative gravitational memory effects might be detectable through precision measurements of cosmic distances or through subtle correlations in the positions of distant astronomical objects. Understanding these effects requires developing new theoretical tools for describing how gravitational waves interact with the background curvature of spacetime. We don't understand whether there might be fundamental limits to how much information can be stored in gravitational fields, similar to the holographic bound that limits information storage in black holes. Such gravitational information limits might place constraints on the complexity of spacetime geometry or the amount of matter that can exist in a given region. If gravitational information bounds exist, they might help explain some puzzling features of cosmic structure formation or provide new insights into the relationship between gravity and information theory. Understanding these limits requires developing new mathematical frameworks for quantifying information content in gravitational fields. We don't understand how the process of gravitational collapse might create exotic states of matter that don't exist anywhere else in the universe. The extreme conditions near collapsing black holes or neutron stars might allow for the formation of strange matter, quark matter, or other exotic phases that interact gravitationally in unexpected ways. Such exotic matter might have gravitational properties that differ from ordinary matter, potentially affecting the dynamics of stellar collapse or the emission of gravitational waves from compact objects. Understanding these effects requires combining gravitational physics with nuclear physics in extreme regimes that cannot be replicated in terrestrial laboratories. We don't understand whether the quantum entanglement between different regions of spacetime might affect the propagation of causal influences and the structure of cosmic light cones. If distant regions of space are quantum mechanically correlated, information might be able to travel between them through channels that don't exist in classical spacetime. Such quantum gravitational correlations might create subtle violations of locality, the principle that objects can only be directly influenced by their immediate surroundings. Detecting these effects would require developing new experimental techniques for measuring quantum correlations in gravitational fields. We don't understand whether the cosmic web of dark matter might exhibit collective gravitational behaviors, similar to the collective electromagnetic behaviors observed in plasmas and superconductors. Large-scale dark matter structures might support gravitational waves or instabilities that don't exist in smaller systems. Such collective gravitational phenomena might affect the formation of galaxy clusters or create distinctive signatures in gravitational wave observations. Understanding these effects requires developing new theoretical frameworks for describing gravitational physics in many body systems with complex geometries. We don't understand how the phenomenon of gravitational self-energy, the energy stored in gravitational fields themselves, might affect cosmic evolution and the ultimate fate of the universe. As cosmic structure grows through gravitational collapse, increasing amounts of energy become locked up in gravitational fields. This gravitational binding energy might play a crucial role in determining whether the universe expands forever or eventually recollapses, but calculating these effects for realistic cosmic matter distributions remains a formidable theoretical challenge that requires new computational and mathematical techniques. As we draw near the end of our extended journey through the profound mysteries of gravity, let yourself sink even deeper into that quiet space between wakefulness and sleep, where the boundaries between the known and unknown become as soft and permeable as the fabric of space-time itself. We've explored far more than 100 questions about this most familiar yet most mysterious force, wandering through territories of wonder that stretch from the quantum realm to the cosmic horizon. And if you've drifted in and out of attention during our exploration, that's perfectly natural, milious, perhaps even appropriate for contemplating a phenomenon that operates beyond the reach of our direct experience. What emerges from this catalogue of cosmic puzzles is not a sense of ignorance, but a profound appreciation for the depth and beauty of the universe we inhabit. Each unanswered question about gravity is really an invitation to wonder, to investigate, to push the boundaries of human understanding just a little further into the darkness that surrounds our small island of knowledge. Gravity shapes every moment of your existence, from the beating of your heart to the orbit of the Earth around the Sun, yet it remains fundamentally mysterious. It's the force that brought the first atoms together in the primordial universe, that lit the first stars, that carved out the cosmic web of galaxies and emptiness, that defines the largest scale structure of everything that exists. And yet, as we've discovered tonight, Nearly every aspect of this fundamental force raises questions that push against the very limits of human comprehension. Perhaps this is as it should be. Perhaps the most profound truths about our universe are not meant to be grasped easily, but are meant to draw us forward into ever deeper contemplation and investigation. Each answer we find about gravity reveals new questions. Each mystery we solve opens doors to even greater mysteries. As you rest tonight, wherever you are in the world, take a moment to feel the gentle, constant pull of gravity holding you safely against the surface of our spinning planet. Feel the way this invisible force connects you to every other mass in the universe, to the Earth beneath you, to the moon above you, to the sun and the distant stars, to galaxies so far away that their light has traveled for billions of years to reach your eyes. You are not separate from the cosmos. You are woven into its fabric through the mysterious threads of gravitational attraction. The calcium in your bones was forged in the heart of ancient stars, held together by gravitational collapse. The water in your body has traveled through cosmic cycles of evaporation and condensation, guided by gravitational fields. You are quite literally made of stardust, organized by gravity into the magnificent complexity of a living, thinking being. And in your dreams tonight, perhaps you'll find yourself floating through the curved space-time around a massive star, or drifting peacefully through the cosmic web, or standing at the edge of a black hole's event horizon, watching the strange dance of matter and energy in the grip of gravity's ultimate expression. Perhaps you'll dream of the early universe, when gravity first began to gather the scattered matter of creation into the seeds of structure that would eventually become galaxies and stars and planets, impossibly minds capable of contemplating their own cosmic origins. Thank you for joining me on this journey through the beautiful mysteries of gravity. Thank you for allowing me to share these moments of wonder with you, and thank you for being part of this global community of curious minds who find peace and fascination in the profound questions that surround us. If this exploration has brought you a sense of wonder, or if it's helped you drift peacefully towards sleep, I hope you'll consider subscribing to Sleep About Science, and perhaps sharing your own sense of amazement in the comments. Where in the world are you listening from tonight? What aspects of gravity's mystery speak most deeply to your sense of wonder? Until we meet again in the quiet spaces where science and dreams converge, may your sleep be peaceful, your dreams be filled with cosmic beauty, and may you wake tomorrow with a renewed sense of connection to the mysterious, wonderful universe that holds us all in its gentle gravitational embrace. Sleep well, fellow travelers. Sleep well.